Hello, everyone. Welcome all to this webinar. I hope you can hear me. If not, quickly pop something into the question box to notify me about this. But I think normally everything should be fine and you guys should be seeing my screen. This webinar will be about the utilization factor and the full-length LTB restraints, which are two new functionalities for the metal side inside V21 of SCIA Engineer. And I will be talking you through the entire technical background as well as everything you need to know to use them inside SCIA Engineer itself. I myself am Jael Verkammer, as you can read below, and I am the product owner for the metal side, but I've also been working for customer support for 3 years now at SCIA. So some of you maybe already know me. All right, before we move into the full presentation, let's go through the workings of GoToWebinar. During the entire presentation, you guys will be muted. This is for the reason, which is the third one on this screen, that this webinar is recorded and will be posted on our YouTube channel. So if you have any questions, and don't hesitate to ask them, but you can drop them inside the questions box. And my colleague Peter is here with me today, Peter van Tendelo, to kindly respond to your questions. So if you want him to feel useful, don't hesitate to ask them. All right, I will put off the camera so you can have a bigger view of the screen, but now you know what I look like. And let's jump into the utilization factor. So the utilization factor is a part of the Semicon Plus not finding the word, project, that's the word I wanted to say, which is an extension onto the current existing Eurocode. And to fully explain you what this utilization factor is and what it does, I will take you back into the entire background, and the background starts with the classification of steel sections. I assume that most of you know it, but I will still explain it to be sure. So for steel checks, we are classifying our sections based on when local buckling will be occurring inside a section. What is local buckling? It's when a flange or the web of your section will buckle by itself before the full capacity of the entire section is reached. For class 4 sections, this buckling will actually occur before even the elastic resistance of your section is reached. For class 3 sections, we will be able to reach the elastic resistance, but then some flange or some web will go and buckle before we reach the plastic resistance. And for class 2, we are able to reach the plastic resistance, but we are not able to form plastic hinges where your section will actually deform so much that the forces will be redistributed along your structure. And that is what differentiates them from the class 1 sections where this is actually possible. Now, to determine when this local buckling is going to occur and therefore in which class we will be, you have some rules for the flanges and for the webs inside the Eurocode. And as you can see, they are dependent on the forces inside the section. If you have full bending or if you have full compression or something in between, you will find different limits for the different classes. The thing I want you to mostly remember is that the more compression you have inside your section, the more severe, more strict these limits will be. Of course, more compression leads to higher chances of buckling. So this is quite logical. Okay, so the fact that different internal forces leads to different section classes means that along the length of your columns or your beams or whatever, you will find different classifications of your section at each level because you have different internal forces. For example, in this column at the top, we will have quite some moment from wind loads, for example, but at the bottom, we have a hinged support, and therefore the forces at the bottom will be full compression forces. For the section checks, it's quite logical which class to use. We will just look at this specific section, check the forces in this section, and use, of course, these forces to determine a class and use the class of this specific section. However, the question arises when we are going to do a stability check, because stability effects like lateral torsional buckling or flexural buckling, these are things where the entire length of your member is of importance. The effect plays over the full length of your member. It's the entire member that is going to buckle. So the question is, what class should we use for these stability checks? And in the Eurocode, as of this moment, we will simply use the highest class found along the member because that's the safe side and we're sure that this is correct. So in the case of this column example I have, we will be using a class 4 for the stability checks. Class 4 means that we will not reach even the full elastic capacity of our section, meaning that we will do a check with reduced resistances. But if we look at this column, for example, actually, let's say that there's a lot of wind, but not a lot of vertical loads. This means that the highest loads will be the moments at the top of this column, whereas at the bottom, yes, we have some compression, but this will not reach the full capacity of this column, and it will mostly be designed on the bedding at the top. So there's a lot of room left at the bottom of the column. Is it logical to go and design this entire length with class 4 just because at the bottom there happens to be a hinge and we happen to have some full compression? Well, the answer is not always. And that's where the extension by the Semicon Plus project comes into play. And they're going to say, instead of simply using the highest class, we are looking for the most relevant section along the member, and we will use the class of this section. And how do we find this most relevant section? Well, that's where we get finally to the utilization factor. So how do we determine the most used section? Like I said, the utilization factor. And the utilization factor is defined as the ratio between the actual design forces in a section and the maximum capacity, the highest possible forces that this section is capable to take. So to determine this utilization factor, we will take the actual forces, combination of forces in your section, normal force and the two bending moments, for example, and then we will linearly increase them until we reach the failure of the section. For some cases, this can be calculated through a simple formula. I've put them out here for you, but actually you can find all this info on our help website. And for other cases, this will need to be done through an iterative calculation, but we will find the limit. And then if we take the ratio, we know our utilization factor. And then along the member, the section for which this factor is the highest will be the section that is the most used and therefore the most relevant to use as a section class for our stability classification. Let's go have a look inside the software. Enough theory for now, and let's open up SCIA Engineer. I will just quickly check the questions. Is everything okay? All right. Nobody's complaining, so I guess everything is all right. Okay. I have here a simple steel hull. I will select the column that you've also seen actually in my presentation. And we are first gonna open our steel settings, where you will now find in version 21, of course, this new option where you can choose the method you would like to use for the stability calculation. The maximum class along the member is the regular Eurocode choice. It will also be the one that is used if you import your older projects. However, if you start a new project in version 21, it will automatically be using the utilization factor. Let me choose the maximum class along the member for now, and let's go to the steel code check, ULS steel code check. All right, and I'm gonna have a look on every section at what the section class is for this section. Okay, so we see that the class varies from class 4 at the bottom with a hinge to a class 1 all the way at the top of our column. So logically, if we are using the normal Eurocode way, we would just take the highest one as the class for the stability check. Let's have a look at this. If I go to the stability check and choose the stability class, indeed, we will use the class 4 for our stability checks. And this leads us to a specific unity check. Let's have a look. Okay, we have a unity check of 0.95, but using the class 4 section properties. Now let's have a look at our utilization factor. So this one, of course, is new in the version 21. You can find it under the stability check, and there you can display the utilization factor along your column. And here we see that all the way at the bottom, where we have the full compression, this compression is actually only 4%, using 4% of the capacity of the section. So this class 4 section is not really relevant for the full behavior of our column. However, we see that the most important sections, the most used sections, are the ones all the way at the top, with the winning one, 0.59, being the top section. And if we go have a look at what the section classes were, we see that at the top, actually, the class is 1, meaning that we are allowed to use the plastic resistance of our section, and also if we would want to form plastic hinges. Okay, so if I now go to my steel settings and I change the classification method to the utilization factor, I will first have a look at what stability class will be used. And of course, it will be the class 1, the class of this highest section. And if we compare the unity check, for example, we see that instead of 0.95, we have 0.86. Why? Because instead of using the reduced properties for a class 4 section, we are now allowed to use the plastic resistances of this section. Last thing I want to show you about this is the output, but let's not do this for every section. I will put it back to extreme global, and then I have put the detailed output as well as the decision tables to have the entire full output for the steel code check. And I will open the preview for you guys. All right. So of course, at first we have the classification for the section check, which is not the one that interests us, but we are looking for the classification for the stability check. And here already you see a few changes. We see that the class 1 is used, not the class 4. And we see that there is displayed some decisive position for the classification, as well as a decisive utilization factor. It gives us a note that we have used the utilization factor from Semicon Plus to decide our stability classification. And then if you have the print decision tables on, which is this one, We will also have a table displayed with every section along your member and the corresponding class and the corresponding utilization factor, where we clearly see the 0.59 utilization at a level of 6.9 meters. Now, if you're wondering why these classes are not exactly the same as I saw previously in the window, that's because this classification is for one specific combination of forces which led to this specific check, whereas earlier we were just seeing the highest classes for any possible combination of forces. So that's the little difference here. But this is exactly what we find here, and we are using class 1 properties to execute the rest of our stability checks. And basically, that's it. It's a pretty simple development for you guys to use, but as you can see in this case, it did save me close to 10% of my material. So I'm pretty excited about this one. I hope you guys are too. And if you if you forgot my explanation or you want to have more information, when you click on it in the Steel setup, you get the reference to the Semicon Plus project where you can check it out, as well as on our help page, you will find all the detailed background information as well. Okay, I hope this was clear. If not, you know where to find the question box. Don't hesitate. And then I will present you our second development, which will go a lot quicker because it's a tinier improvement, but it did win our customer vote, so it must be important as well. And this is the full-length lateral torsional buckling restraint. Now, as you know, we already had lateral torsional buckling restraints, so I will not be explaining those. What is new is that we have an option to restrain this member along its full length. You could maybe do this previously by putting a very high number of LTB restraints onto your beam, and it would act pretty much the same way. But now it's just way more simpler. You just hit the fully restrained option, click OK, and select the beam on which you want to add it. And then the symbol with the 2 arrows will indicate that your beam is restrained along its full length, as opposed to, let's say, if I were to add 5 of them here, as opposed to in these precise locations. If you switch from a precise location to fully restrained, it will remember it. So if I switch back, I get my 5 LTB restraints back. So if you click it by accident, you're not going to lose your input in any way. And of course, you need to choose the top side of the beam or the bottom side of the beam to be restrained. Or if you want both of them, in this case, as you can do as I did and add 2 of them. For now, I will delete this one, and I have added in this tiny, easy project 2 load cases, which are exactly the same. One is going up, one is going down. So in the first case, our compressed side will be the bottom side, which is where the beam is restrained. So this should give us some better results than the second case, where it's the top side being compressed and our lateral torsional buckling restraint on the bottom side will not have any effects. So let's go have a look at the check. Let's start with the load case going up. I will change the view as well. So in this case, our LTB restraints should be helping, and we see a unity check of 87%. And then if I switch the load around, our buckling restraints will of course no longer be helping us, and we see indeed a much bigger unity check. Just to prove to you that that's actually really how it's working, I will add a lateral torsional buckling restraint again on the top side. And if we refresh this, we get the same check as we got previously, right? So your lateral torsional buckling restraint needs to be on the right side, of course, for it to get get an effect. And it's simple as that. If you add a restraint on the entire length of your beam, well, then it can no longer buckle in any way. So what you will see in your check all the way at the bottom is that the lateral torsional buckling check is neglected because your member is fully restrained laterally. And yeah, that's basically all I had to say about this. So that's perfectly in my 20-minute time frame. Little round of applause for myself. I would ask, are there any questions? But normally you should have already asked those. I, however, have not seen any enter. So I guess my presentation was pretty clear. I will, however, ask you if you have some time left. Oh, sorry, I need to scroll through there. And if you want to have some voice in what the metal department will be developing next for you, if you want to, please take some time to fill out this little survey. I've also shared the link in the chat if you don't want to scan the QR code with your phone. Just 3 little minutes to give me some feedback on what would be important for you to be developing on the steel side, on the timber side, composites, and aluminium. And I thank you very much for your attention today, and I hope to see you again on the next webinar, which is about FEM for cross sections and the bow imperfection defaults. All right.